The Big Bang theory, while widely accepted, is not necessarily the beginning of everything. The origins of the universe have long been a topic of speculation and an intense discussion in cosmology and theoretical physics. According to the Big Bang hypothesis, the universe began from an infinitely small, dense singularity around 13.8 billion years ago, rapidly expanding to create the universe we know today. However, there is an increasing body of alternative theories that challenge this view, suggesting that the Big Bang may not fully explain the origins of the cosmos. Time itself might have no beginning, and this idea challenges the traditional understanding of cosmic genesis. The Big Bang theory is supported by the redshift of galaxies, a phenomenon in which light from distant galaxies is shifted towards the red end of the spectrum, indicating that these galaxies are moving away from us. This observation fits well with the notion of an expanding universe. By measuring the degree of redshift, astronomers can estimate the distance of galaxies, providing strong evidence for the expanding cosmos. However, despite its compelling evidence, the Big Bang model has some significant flaws. One major issue is its inability to explain the circumstances of the universe before the Big Bang. The theory's singularity implies an infinite point of temperature and density, where the laws of physics as we know them break down. This raises the fundamental question of what existed before the Big Bang, and how the cosmos came to be. The concept of a singularity, with infinite temperature and density, presents serious challenges for understanding physics. It's difficult to imagine what happened at the exact moment of the Big Bang, since the physical laws we understand cannot be applied under such extreme conditions. The horizon problem is another dilemma. According to the Big Bang theory, distant regions of the universe that are now far apart were once close together and shared information. However, this uniformity is puzzling because the regions couldn't have had enough time to exchange information. The cosmic microwave background, CMB, radiation's consistency over large distances creates a problem that challenges the standard Big Bang model. To explain phenomena such as gravitational interactions among galaxies and the universe's rapid expansion, the Big Bang theory relies on the existence of dark matter and dark energy. However, the nature of these two components is still poorly understood, leaving a vast gap in our comprehension of the universe's structure. Cosmic inflation theory, which seeks to address some of the Big Bang's shortcomings, raises its own unresolved questions. Specifically, the process that drove cosmic inflation and how long it lasted are still topics of research and debate. Though the CMB radiation supports the Big Bang theory, certain anomalies within it, such as temperature fluctuations and unusual alignments, challenge the interpretation of this data. These include areas of the sky where the CMB appears colder than expected, and the so-called axis of evil, a strange alignment of these cold spots. These anomalies have led some to consider alternative causes, such as exotic physics or phenomena beyond our current understanding, as they don't fit neatly within the Big Bang framework. Additionally, large-scale structures like cosmic voids, filaments, and superclusters seem to contradict the Big Bang model's prediction of a smooth, homogeneous universe. The existence of these complex patterns suggests that the universe may be more hierarchical and organized than the standard Big Bang theory can explain. At extremely high distances, galaxies seem to be moving in ways that don't align with the predictions of the Big Bang model. Studies suggest large-scale flows or unusual velocities that are difficult to reconcile with the idea of a uniformly expanding universe. When it comes to explaining the redshift of galaxies, the Big Bang theory attributes this to the expansion of the universe. But alternative theories, such as the tired light theory, propose that redshift occurs due to interactions with matter or photons during light's journey through space, not because of cosmic expansion. Although this theory is largely dismissed by modern cosmologists, it still represents an alternative perspective. Another theory, intrinsic redshift, suggests that redshift could arise from gravitational effects within galaxies themselves, rather than from the universe's expansion. Despite these alternative theories, supporters of the Big Bang model continue to emphasize its effectiveness in explaining the universe's development. They point to the model's ability to predict key phenomena like the abundance of light elements and the CMB, which have been confirmed by observation. Big Bang proponents argue that the theory remains the most coherent explanation, incorporating new mechanisms like inflationary theory to account for anomalies. Alternative cosmological theories, such as steady-state theories, plasma cosmology, and cyclic models, challenge the Big Bang. These theories propose different explanations for observable phenomena, though critics argue they often rely on speculative mechanisms or lack strong empirical support. Some of the key challenges posed by alternative models are their failure to explain the abundance of light elements or the cosmic microwave background radiation, which remain two pillars of the Big Bang model. Critics of these alternative theories point to Occam's razor, which suggests that simpler, more straightforward explanations should be preferred when all else is equal. Despite the criticisms and complexities surrounding it, the Big Bang theory is still regarded as the most comprehensive and reliable explanation for the observable data we have. However, our understanding of time and reality may be dramatically affected by concepts like a timeless cosmos, which challenges the idea of linear time and could reshape our perceptions of causality, free will, and human existence. A timeless universe would raise deep, philosophical questions about causality, selfhood, and the nature of change. Without time, the concepts of identity and continuity may no longer make sense. Moreover, in a timeless framework, the lines between objective and subjective reality, or between material and immaterial existence, might blur. Reconciling these scientific ideas with metaphysical concepts of timelessness poses a formidable challenge. Theories like quantum physics and cosmic inflation, along with ideas from cyclical cosmology and quantum superposition, hint at a reality that doesn't conform to traditional notions of time. In this reality, events could occur simultaneously, and causality could become nonlinear. Philosophical and religious traditions have long grappled with ideas of timelessness. For instance, Parmenides believed in an eternal, unchanging reality. These metaphysical views provide alternative frameworks for understanding existence, which might offer new insights when considered alongside modern scientific theories. Ultimately, reconciling scientific theories with metaphysical ideas of timelessness could lead to a more complete and cohesive understanding of the universe. By combining perspectives from different fields, we might gain new insights into the fundamental questions that have intrigued scientists and philosophers for centuries.